Okay. I believe I am streaming. Wow, did that go live immediately? Look at that. It sure did. Okay. Wasn't expecting that so quickly. Let me copy this and post it here. Hey all, Smitty Halibut here. Today we are going to be talking about egg beater antennas. I'm live streaming on YouTube to design a feed point system for an egg beater antenna for SatNOGS operation. Okay. I think I'm live. All right, let me bring up my live stream page so I can actually see what's going on. Oh, shoot. Customers are receiving buffering. Enough video to maintain. Oh, this may not work out so well, because Skype was giving me all kinds of troubles yesterday. So, let's grab a ping. Pretty ping. Halibut.com. All right, let's keep an eye on what my packet loss is like. Hey, I've got a viewer. I don't know if it's considering me that viewer. It might be. Hello, viewer. Whoever you happen to be. Hi, I'm Mark. N6MTS, Smitty Halibut. I used to do live streams all the time, but I haven't in a while. And I had an idea, well, sort of. I blame AI6YR, Ben, who we just did a recording with last night on for the Ham Radio Workbench, and he was talking about SatNOGS and got me thinking about egg beater antennas. Let me turn off some of these tabs. And then I'm going to switch over here so that you can see my desktop. We were talking about SatNOGS and what kind of hardware it takes. And that episode is going to be dropping, it might be as early as this coming Tuesday, which would be, let's see, 18, 19, 20, 21. It might be March 21st, or it might be a later episode. I honestly don't remember when that particular episode is going to drop. But this is him down here, AI6YR Skyscanner, and that is his SatNOGS receiver. I live up in this area over here, and there's nothing, right? Like, he's my closest receiver, Ben is, but I live up in this area here, and there's nothing there. And so I would like to set one up. And when you look at SatNOGS, there's all kinds of expensive directional pointy antennas that you can do, or you can use inexpensive egg beater antennas. And so I looked up egg beater antenna designs last night, and they're basically two phased full wave loops. Full wave? I think they're full wave loops that are 90 degrees physically out from each other and as well electrically out from each other. And then there's a ground plane underneath it. And so there are several documents on how to build an egg beater. Let's see if I can find a better picture. So this is the picture that kind of inspired me. So this is a PVC cap, and you've got the pieces of the loops come in, and they kind of screw to the top of that cap. Make it a little bit bigger for the stream. And they screw to the top of that cap. And inside, there's really nothing in here, but I was thinking that we could stick a circuit board up there and have it do provide the function of these ferrite beads, which are common mode current chokes, and also a place to do the phasing lines between the two loops. So the phasing line is a quarter wavelength of coax. So these antennas are not multiband. They are monoband, so you have to cut this piece of coax to 1/4 wavelength, which means that as you go away from the frequency that coax was cut for, it becomes more or less than 1/4 wavelength, and you start running into phase problems. It ends up like squooshing your radiation pattern. But since I'm only looking at a receive antenna, not a transmit antenna, I don't need a high power balun like this. So we can use a binocular core, which is a lot smaller, a lot more lightweight. It works just as effectively, arguably more effectively than this, but it can't handle the power of transmit, and we don't care about the transmit. And then the other thing I want to include in there is an LNA, a low noise amplifier. And here is an example of the RTL SDR LNA, and it is, I don't know if I can't tell from looking at the artwork here whether it's using that chip, but there are chips. 3018 is the one that I'm thinking of. It's an 18 dB LNA. It's meant for like cable subscription services. It's 75 ohms, but it's close enough for our needs. But it's just a single chip, and then you have to get the power off of it. Yeah, I can't point to it with my... Anyway, you have to get the power out of it using a bias T, and then you filter that power, and then you feed the power back in through another inductor into the input, well, actually the output of the amplifier. The antenna comes in over on this side. And then it goes through the amplifier chip and then back out to the output, which is toward your station. So there are very few components here, and I can integrate that into the board that I'm looking at. So, this would have been good. So this goes to your station, this goes to the antenna, DC goes across this inductor, gets filtered, and then you can also, on this one, you can provide external power instead of a DC bias power, or bias T. I won't do that, I'll require a bias T. So the inductor comes in, it gets filtered, maybe put a power LED on there, actually I probably won't, and then more filtering and feed it back in to the amplifier here, and then that capacitor just allows RF to go straight through. Because the whole point of this stuff up here is to filter the RF to ground, is to shunt it to ground. And then diodes. Interesting. So those are probably just like static buildup dissipation diodes. So and they'll also protect the front end of the amplifier. That if you're transmitting with too strong of a signal nearby, the power will dissipate. The voltage will get high enough that the diodes engage, and they'll just shunt that power to ground, and it protects the input of the RF amplifier. So I can put this style of an RF amplifier on the board with a binocular balun and spots for... Nope, you don't need to be seeing that either. With spots for the phasing loop. So let's get started. And I'm going to create a new KiCad window. And we're going to do a new project. Where am I going to put it? I'll do over here. And we'll create a new directory. We're going to call it egg beater feeder. Sure, let's do that. And then we'll call it egg beater feeder. And that is creating the project in KiCad. And now we're going to open up our schematic. And yeah, so there's an empty schematic. Always an interesting prospect. Let's start out with our feed point. We have a coaxial connector, and I'm going to flip it around. Do that. We'll give it a ground. All right, so the first thing coming into the coax, let's see here. I want the balun between the antenna and the LNA. The LNA should have the common mode currents already removed. So let's go straight into the VNA first. little small for an inductor. And I'll come back and figure out values for these in a bit. C small. And that is my capacitor, my DC blocking, AC passing capacitor. So this one I know I want to be like 1 nanofarad. Value, just make that an RF choke. And I'll come back and figure out what that value is in a bit. So my RF is going to go from here and then straight in through the cap, and then we'll figure out where it goes from there. But I need to filter out any noise from my DC first. So let's put some more capacitors in here. I'll put it down here. And actually, a 1 nanofarad is probably a good choice to start out with. Let's also put a value, a 1 microfarad. That'll probably be good. Again, we are making because I just had a viewer join, we are making a feed point for an egg beater antenna. Coax in, DC or bias T power out to go to an LNA, and then an LNA will go right here. And then after that, I'm going to put a balun, a small receive-only balun, and then the phasing stuff needed to be able to feed 2 full-wave loops out of phase to make an egg beater antenna. All right, so there's my power. We'll call that plus 12 volts. And then I will need to... what do I need to do here? 3018 LNA. I am mini circuits. Shoot. No, I think that's using the 3018 chip. What is the part number for the 3018 chip? Is it an NXP? I think that's the one. BGA 3018, that's it. Okay. Does KiCad have a BGA 3018? Look at that. Is this in my... What library is this? Yep, Smitty. So I have created this one already. Okay. So there is our BGA. I feel like a huge dummy watching this. Hey, Ray. No, you're not a dummy. I have spent a lot of time thinking about this stuff. So if you have questions, by all means, pop them up. That's why I do live streams like this, is so that I can figure out what people are interested in seeing and explain things and peanut gallery and all kinds of fun things like that. So hit me up with any questions that you have as they come up. Also, there weren't a lot of people on the stream when I started it because I didn't announce it. I just kind of started it up. So all my explanation of what it is I'm trying to accomplish happened before most people were on the call. But what I need to do first is look at this and look at the data sheet, because I don't remember what the feed voltage is. Yeah, it's 75 input, but it's close enough. From 5 to 8 volt supply. Okay. So I should probably put a 5 volt regulator in here as well. Because most bias T power supplies, actually, that's not necessarily true. RTL, SDR, Dongle bias T. Smells everywhere. One of these. That may be 5 volts natively. You know what? I think I'm just going to run it straight off of that. Oh, there it is. 4.5 volt USB powered bias T. This allows the RTL SDR to power low LNAs and active antennas through the coax cable. Can be enabled in software because that is the one that I plan on using. 4.5 volts is probably close enough. Not you. That's the data sheet I want. Okay. Quick reference, supply voltage, but these are... Oh. That's typical 8 volts, but we're only getting 4.5. Okay, so maybe this is not the chip I want to use. Okay. So let's go back over here. RTL SDR. SDR bias T's and enabling the V3 bias T. Okay. But bias T hack, new videos. Start featured articles. Shoot. RTLSDR.com makes their own, there it is, search, LNA. They make their own LNA, and I'm trying to copy that design. Dongle with dipole, dongle only. Flight aware, RTL, triple filtered LNA. That's the one. Please restore RTL for ordering. Are these might not be open source. Maybe this is not what I want to copy. Oh, shoot. Oh, I'm not trying to steal anything from anyone. I just kind of assumed this was open source, and maybe it's not. All right. Then let's do it this way. Open SDR LNA schematic. Publishing the schematic, it's going to be good. LNA for RTL base SDR receivers. Yeah, see, this is how small an LNA can be. Mini circuits PSA 5043 is an LA used. Oh, shoot. Okay, so PSA 45043. PSA 45043. Mini circuits. How much gain are we talking? And that's 50 ohm. Power output at 1 dB. Compressions up to 21 dBm typical. That's a lot. 18.4 dB typical. Okay. Supply voltage 3 volts. There we are. Or 5 volts. Okay, so somewhere between 3 and 5 volts. So I can probably just run that straight off of the bias T from my SDR. Electrical specifications. Yeah, it specifies parameters for 3 volts and 5 volts. So 4.5 will be fine. It'll be somewhere in between those two. All right. I am willing to go with that. Now, let's go over to KiCad. What's the part number? PSA 4. Let's start with that. PSA 4. Nope, that's not it. 5043. Hey, look. I've already laid that one out before, too. SPF 5043. 50 to 404 gigahertz gas FET, low noise mimic amplifier. I've already done that one too. Sweet. All right. So I'm going to use that one instead. No. Go away. Okay. So now I need to filter this out and feed it back in to the DC. So we'll do another one of those. Let me make sure that that's how it's supposed to work. Okay. Show me a typical circuit. RF in, RF out, and DC in. Yeah. RF out by blocking cap and supply voltage via RF choke. Yep, okay. So RF out, 3 to 5 volts, and another cap there. Recommended application circuit, no resistance of L1 is very low resistance, yes. So I'll have to pick those components carefully. Are you going to give me recommended values for those? No, of course not. But that at least gives me... Yeah, okay. So I'm pulling this 3 to 5 volts off of the RF input. So there's an RF choke that comes off here for the bias T. That provides us our voltage source. Then we filter it with these capacitors to take off any noise, and then we feed it right back into the circuit. Yeah. Okay. We got a 1 nano. You know what? Value. 100 puffs is only 1 decade out. So if I do 100 puffs and then value 10 nano and then 1 micro. All right. So what I did is I just kind of spread these out. So it's 100 times between each of these. 100 times 100 puffs brings you to 10 nanos, and then 100 times 10 nanos brings you up to 1 micro. So we've got 2 decades between each stage of filtering, and that'll help respond to lots of different frequency ranges. That's not 12 volts anymore. In fact, you know what? I don't even have to label that because the only place I'm going to use it is right there. Like that. Okay. Okay, cool. There's my LNA. Wrong way. That goes like that. Yeah, that would have been embarrassing. So the output of the LNA is going to my feed. Or RF out. There we go. Let's make this an SMA. Connector, coaxial, SMA. I think that's the outline I use. There are a bunch of SMA outlines here. Okay. Good with that one. They're roughly equivalent. For those who are just joined us, feel free to ask me any questions you want in the chat. I am watching the chat. This is supposed to be kind of an interactive thing, so I would love to answer any questions you may have about what in the heck am I doing. Okay, balun. We do have baluns, don't we? 1-to-1 RF transformer, unbalanced to balanced with integrated DC blocking capacitor. Oh. Those are chips. No. Impedance match multifunction integrated ceramic passive component for yeah, okay. No. All right. I mean, from a schematic standpoint, all of these are fine. Transformer. Really, that's what I want. Is a transformer for now. Yeah, getting one of these mini circuits. But finding something that's suitably wide band for what I'm trying to accomplish is going to be hard. But that's, yeah. I want a 1-to-1. Well, curses. I'll have to spend some time looking at Mini Circuit's website to see if they have other frequency ranges that come in a similar ADT1. Yeah, see, here's one, but it's 75 ohms. Core and wire transformer. Yeah, they're all that. Oh. No, that makes sense because with the higher impedance, the 75 ohm impedance compared to the inductance of the transformer, it is going to be able to operate at a wider frequency range just by the fact that you're feeding it with a 75 ohm system instead of a 50 ohm system. I'll bet you these are the same transformers. Well, poop. All right, so let's do this. Products. Couplers. Transformers and baluns. We'll do 140 and 500 at 50 ohms. Impedance ratio 1. There we go. Yeah. 20 to 12. Ooh, that's nice. What is this? Yeah, see, that's what I'm talking about. When you're not having to do transmit power, this level of transformer works fine. Or do I just make my own outline that, and then let the customer or the user wrap their own toroid? See, at $3 though, these aren't that expensive. And that's in small quantities. Got to do $1.50 at 100 quantity. Okay. Which one was that? TC1? TC1 113M. What is that one? Oh, that's a module. $60. No, thank you. Excuse me. There are lots of versions of this 13. What's the difference? Power handling? Size? These are all pretty inexpensive at quantity. Impedance ratio 1, frequency range plenty wide. Oh, insertion loss. 1 dB in the range that we actually care about. Okay. I think I'm okay with that. So these are the two rows that apply to us the most. So, oh geez, well less than a dB of insertion loss. Okay. Yeah, I'm okay with that. All right, so that's definitely a good option. Specs looks very similar. What is the difference? RF power, 1/4 watt. What's the RF power on this one? 1/4 watt. DC current, 30 milliamps. 30 milli. Yeah, so like 64132. 64132. These look very similar. Like almost exactly the same. MG2 versus MX. Oh, it's the top hat. Or the M. This is more expensive. Yep, all the same specs. So my guess is just a different outline on each of these. Yeah, okay. K-Style AT2241A, K-Style AT1521, and the K-Style AT224-3. Okay. So, I don't think we much care. For our needs, these are all sufficient. I would like... Yeah, I don't know. So, what's J? 0.19. J here is 0.19. This is even literally the same output or outline. 0.19. Yep. K is 0.03. There's K. K is not even listed. Sweet. .03. Yeah, so these are the same outline. Okay. For the purposes of what I'm doing right now, I don't need to select between them. I just know that I'm going to go with a TC1-1. Let's head over to KiCad and see if we've already got that. TC1-. Nope. Oh. Yes! That is not the same brand, but that is the same transformer. ETC1-1-13. That is exactly what we want. Perfect. All right, there's our balun. So I think they do want me to DC block the input there as well, so we'll do that. And then I think we just do this. All right, so there's our balun. And actually, let's do this differently. Okay. And then I think I also want to ground that. Okay. Did it say anything about that? There it is. So primary dot. I don't care too much about the dots. 6 and 1, then 4 and 3. No, sorry. 6 and 4 is primary, 1 and 3 is secondary. Seriously? Yep, you use different numbering. All right, so 1 and 3 are secondary, and then 2 is between them. So 1, 2, 3, and then 4, 5 is empty, and 6. Yeah, it's numbered totally differently. So 1, 2, 3, 4, 5 is empty, and 6. So I want 3, 4, and 5 to be... No. 2, 3, and 4 to be ground, so I can just ground plane this, and then 1 and 5, which by the other numbering is 1 and 6. So I want 1 and 6 because 1 is secondary dot and 6 is primary dot. So that's what's going to be my choke going through there. Okay, yes, so I want... Okay. So I want 2, 3, and 4 to be grounds. I want 1 and 5 to be my signal. So 1 and 5 are signal. 2, 3, and 4 are ground. Perfect. Okay, we're good to go. Hello. I see viewers coming and going over time. If you've got any questions, feel free to hit me up in the chat. I am designing what I will hope to be a circuit board that goes at the top of a egg beater antenna. Really quickly again, let's show what that egg beater looks like. Where is it? Is that it? That is one of them. There we go. An egg beater antenna looks like this, where you've got 2 full wave loops that are 90 degrees out of phase from each other, both physically and electrically. And then there's a ground plane underneath it. And for receive only, they commonly get added in LNA because their gain is very low compared to like a directional antenna. So, and then you feed them electrically out of phase by sticking a quarter wavelength between the 2 loops. Between the 2 feed points of the loops. So one loop is fed directly from your feed line, and then there's a quarter wavelength of coax, and then you feed the other loop out of that, and that turns that, it delays it by 90 degrees. When you're wanting to transmit on them also, you need a balun that can handle lots of power, common mode current choke that can handle lots of power. But I am intending this to be a receive only, so we are going to go with a transformer that is only good for receiving. Well, I guess technically up to 1/4 of a watt. It can handle up to 1/4 of a watt, but I'm intending it to be a receive only antenna. So, yeah, and then we're also integrating an LNA. So that's what we've got here. This is the coax down to the station. Pull the DC off of it, filter the heck out of it. Your RF goes straight through. Then you put that DC back on the line. Here's your LNA. The input to the LNA is coming from a balun, and now is where we feed our antennas. I want to use screw terminal. We're going to have 4 single port screw terminals. And so we're going to label that one 0 degrees. And we're going to label that one value 90 degrees. Value 180 degrees. And then 270. Value 270 degrees. Okay, so those are our 4 feed points. So one, or we'll call 0 degrees to go straight off of the feed point, which means that, actually, you know what? I'm going to treat this like a balanced antenna at this point. Okay, because it kind of is. So we're going to move that one out of the way. We're going to move that one up there. Actually, we'll move all of that. Get it closer because it doesn't need to be that far away. And there is your in-phase antenna feed point. Enjoying so far, but your audio keeps dropping out from time to time. Hey, Paul. Yeah, my... I've got a ping time. See all those red exclamation marks? All of that red are packet loss. So my ISP is giving me some serious fits. And I don't know why. I've rebooted my router and a couple of other things. My best guess is that it is moist and wet in places that don't like moist and wet. But here we are. So that's what I'm fighting with. If we see lots of lag and drops and whatnot, that's what's causing it. When we were recording the show last night, Skype was not dealing with that packet loss very well at all and kept kicking me off of Skype. Like sometimes while I was in the middle of saying things. I mean, it's like, I'm used to a peanut gallery. If you want me to shut up, just tell me to shut up. But Skype has to be all passive-aggressive about it. So anyway, it's good to see you, Paul. Okay, so now we need to make a phasing loop. So what I'm going to do is I'm going to copy this and say that that is what? Why did that not? There we go. And that is going to be one end of your phasing loop. And then the other end of the phasing loop is going to be right here, and we are going to connect that terminal to it and that terminal to it. Okay. So we got our 2 loops of we got our 2 full wave loops over here for the egg beater. We've got a, come on, get in there. We've got a 90-degree phasing loop, which is not going to be on the circuit board. It's just going to be 2 connectors that you connect the quarter wave loop or quarter wave length of coax to. Then we have a balun, which is going to take those and get rid of any common mode currents that may be there and turn it into an unbalanced signal. Then that goes into an LNA. The LNA is powered by the bias T, and that's going to go to an SMA port down to your station. And I think that's all that's needed. So we just have a bunch of capacitors that we need to figure out what to do with. So let's annotate that, and then we're going to come in and put some component sizes to these. I promised myself I would not do 402s anymore, so let's do these as 603s. No, none of these are electrolytic. 603s. 603s. Oh, the RF chokes, those may actually end up being 805s. Let me see. We'll start out with 603s on those. And then screw terminals. Yeah, mounting holes. I like M3s. I do everything with M3s. Okay. The phasing loop. We got to do something else here. Although a phasing loop out of SMA cable, there's going to be some loss in there, but that may be an easy way of doing it. I want to create my custom outline for this. Okay. So I had an idea for this. Let's go make an outline. So I'm going to come down to the Smitty. Where is it? Wait, what? Oh, nope. Just kidding. Libraries. Libraries. There we go. And new component. What am I going to call this? Coax direct. Oh no, I need to pick a size. RG316 direct solder. And we'll call that a through hole. So what I want to do is the circuit board is going to be at the top of a PVC cap, and then I want to have the coax come down and loop back into it. And so what I was thinking of doing is making an outline that is a hole in the board that you strip off some of the outer insulation and you pull back the shielding, and you slide the center insulator through the board, and then like fold the center conductor over, and it solders on one side of the board, and then the kind of the frayed out shield gets soldered on the other side of the board. And so you don't have to worry about whether you've got little strays of your shielding connecting to your center pin or anything like that. You know, like one side gets, or one of the connectors gets soldered on one side and the other connector gets soldered on, or conductor gets soldered on the other side. So next thing I need to do is measure the diameter of, or I can probably look it up, RG316 dimensions. Can you show me dimensions? Nope. I'm looking for something that'll tell me the diameter of that center dielectric. Interconductor, conductor type, dielectric. Ooh, there we go. 0.06 inches or 1.52 millimeters. Okay. 0.06 inches. So let's start out with a hole That is 0.06 inches. Through hole, SME edge connector, non-plated through hole, mechanical. Pad shape circular. 1.524. Is that exactly the size I need it to be? 1.52. Dang, look at that. It was already defaulted to that. We're going to make that 1.55. We'll give it a little bit of slack. Oh, no, that was the pad size. Okay. And then the hole size is going to be 1.55. That's what I want. And it's probably going to complain about those numbers being the same. I don't know why it bothers, because it's a non-plated through hole. Non-plated. There's no copper. I don't want any copper. Just drill a hole. But it doesn't. Okay. Warning. Pad drill will leave no copper, or drill shape and pad shape do not overlap. Yep, I know. So, go away. No. You go away. Okay, so there's that. Now I do want a surface mount. Let's see here. SMD position. Nope, circular. We're going to do what? 3 millimeters? Why am I working in millimeters? I'm American. SMD 0.1 inch. Yep. And this is going to go on the front. So this is our ground. Now I want that to be a little bit bigger. First off, let's also switch to an American grid. This stuff I need to learn. So cool. Oh yeah. Because you wanna be learning KiCad. Paul says this looks like the stuff that I need to learn. So cool. Yeah, Paul and I have been chatting in email about a project he's working on, and yeah, this is kind of right up your alley. Nope, too big. 1.5. That's probably not too far off. That's even a little bit big, actually. 1.5, 4. That looks better. Okay, and then we're going to do another one, but this one is going to be a SMD, and it's going to be rectangular. And we'll make that 0.3. No, that's way too big. 0.2. 0.1 wide, 0.2, yeah. Okay, all right. Oops, nope, wrong side. Back copper. Nope, that's also way too big. Okay, so we'll do 0.05 and 0.1. Okay, so the idea being that you insert the coax from the front surface, and you kind of splay out the shield and solder it to the exposed surround, and then you've inserted the coax or the center insulator through the circuit board, and then now you've got a little tip of wire, and you just kind of bend that over and solder it to the pad on the bottom. Because I'm explicitly going to be using this where I want the shield to go one direction and the center conductor to go a different direction. So this actually works out pretty well for me. I'm wondering whether I want to make this just a rectangular pad go in the other direction. like put one of these, edit, and put that on the front layer, like that. And so now you just kind of take the shield, kind of twist it off, pull it off to one side, stick the cable through, and then put the center conductor down the other side. I think I kind of like that better than the circle. And it actually, I might come back and decide to put that at 90 degrees. No, maybe. You know what? I'm going to do it this way. Okay, so edit. We're going to make this pin 1, and we're going to make this pin 2. There we go. That got weird. Why did that not? Bad shape, rectangular. Okay, that's what I expected to look like. Okay. All right. Coax RG316 direct solder. Let's do that. And then we'll close this and we'll go back to here. So this is where you specify what parts a given schematic component is. And now we go down to the libraries, the ones that I just created. Coax RG316 direct solder. And you can look at that component, and that is the one that we just created. Okay. Okay. Let's open up the board editor. Not up there, here. So our schematic is good. Well, in theory anyway. Let's load the board from the schematic. And now we got a bunch of parts. Okie dokie. First thing we need to do, I think I already know the answer to this question, but let's look it up anyway. PVC pipe dimensions chart. Because my thought is that this is going to end up on the inside of a PVC cap. And yeah, so this is the chart I was looking at earlier on my phone. A 1.5 inch PVC pipe has an outer diameter of 1.9 inches. And since I'm planning on this going in the cap, which fits on the outside of the pipe, the 1.9 is the dimension that we have to work with. I don't want it to be a snug fit, so I'll probably do like 1.7 or 1.6, and that's diameter. So let's go do edge cuts, which is how you specify the board dimensions. And damn it, not millimeters. I'm an American. So if we did 1.6, that would be 0.8 inches radius. But if we did 1.6, yeah, so that gives us 3/10. A little bit of wiggle room. Let's see if we can fit everything in there. Okay, so that's my board. Let's go put our terminals. Where we want them on the board. So that's the 0. That's the 270. Actually, let me put these in places that make more sense logically to me. Well, are we doing math or are we doing compass? Oh, we'll do math. 180 directly across from 0. Is that on the center line? It is. Okay, and then 90. All right, so those are my loop feeds. My SMA, I'm going to want someplace where it's relatively easy to get to. But I also need to make space for, for all the components that are going to go around it. Okay, so we are looking at the circuit board as it will look when we are looking in the end cap of the PVC. So that means the SMA is going to be on the top surface, and we want these phasing arrays. Let's see here. Yeah, I think I do want those at 90s, and I'll show you why in a second. Con BNC coax, the direct solder, there we go. Save, okay. So we've made that change, and then we come in here and we replace footprints with those specified in the schematic. Oh, but no, that may not do it. Yeah, I gotta refresh. Oh, there's another way of doing that. What is it? Well, the cheating way is to just delete them and then reload, and it will pull them in again. Yep, there we go. Okay, now the reason I want, one at a time please, the reason I want that this way is so that I can, which one's which? I think I want them in this orientation. So I can put these very close to each other in the center. Maybe not that close, because I don't want a lot of phase difference between these. So that's probably pretty close. The problem is we need to make sure that the shields don't touch each other. So with that, if I come over here, all of this is RF, isn't it? Okay, so one of the first things I need to do is I need to board setup. I want to, nope, net classes. Track width is 0.039 inches. With the clearance of 00787 results in 50 ohms. All right. Oh, but I'm not going to be, maybe I will, doing a ground plane. But that's, yeah, okay, doesn't matter. So let's see here. This one will come like that. This one will go like, that's way off. Why is that way off? All right. So this may not be as simple as I thought. Yep, I lied. Let's go back to the 90s. Or the 180s, the straight across. Libraries. That one. Put that back over here. Save. Close. And then we'll delete that again, and delete that again, and delete that, and delete that. Delete that. Delete that. Okay, now reload from the board, which will pull in my components again. And now I can rotate that like And I want my centers to still be where they were. Oh, shoot. Yes, there we go. Okay. So we've got one side. Yep, okay, I think that's what I want. And then there. Okay. So that's my phasing loop. And we've got, you know, that much of an error. What? This does not look right. Where's my center? That's my center. So I've actually marked that as center. Okay, U. There we go. U. Okay. Ow. I think that is what I want. And then from here to there, and from here to there. Okay. Now, I want you to move over into this corner because that's where we've got more space. Okay. So, first off, let's turn off all that text because I just don't care. Make it invisible, turn off the reference, the values, and the footprint text items, and go away. Bloop. Much cleaner. Wait a minute. Why did... Oh, bloody hell. Because you're only selecting the pads. Why are you doing that? Okay. Fine. Make me do it the hard way. There we go. Edit text. Same thing. Make them invisible. Go away. Okay. Thank you. Seriously? I missed you too? There we go. Are we done? That looks good. All right. So the first thing we need to do is which one? No. That is the one. Okay. Actually, let me work from the center back. So I think you will go... Seriously? Those are crossed. Poop-a-doop. Okay. It might be as simple as doing this. Swapping those around. And then reloading. I think that will do what I want. Make this a lot easier to feed. Oh. So I just changed which so I changed half of it. That was the problem. Okay, so I also got to change this part. Okay. Save that. And now reload here. Okay. Yep, that was it. All right, so now I can do that again, and I can come here and I can do that again. And now this becomes a simple feed. Except for the fact that that needs to... Oh, yep, that needs to via down. Vias are always sketchy at RF. Nah. There we go. All right. From there, I think I can define a ground plane. We're only going to do the top layer. We're going to do ground. Oh, actually, wait. Yeah, we'll only do the top plane. I'm going to do with solids, and we'll do this. Okay. Let's try that. Okay. So the question is, can I keep my stuff within that space? Only 2 layers. And I got 3 here, so one more. Okay. So let me turn that off. Okay, so there is our choke, and I am going to bring this up, but put it on a different screen so that I can see it as a reference. But you won't be able to see it. That's okay. So C3 is my RF pass cap, so that's going to go... Where does that go? Oh, that goes... Oh. Let's figure out where the LNA is going to go. Not that, you ninny. So it's got to connect to that, which is going to feed that. Okay. Shoot. So actually, okay. So RF comes out of here, goes through the first DC blocking cap, goes into the LNA, comes out of the LNA, goes into the second DC blocking cap, into the balun, and then from the balun into the first antenna pair, then from there into the phasing loop into the second antenna pair. Okay. Now I need my DC filtering, and that RF choke is going to feed that. And then I just need my filters. So let's see here. We want to start with that one. Nope, piss off. That one closest to, and then the 10 nano next to that, and then you come down here. And the 1 micro there. I think that's what I want. First off, let's get rid of a lot of this extra text that we're not using. Edit text and graphics. Keep the designators, but lose the values in the other text. Make it invisible. Go. Okay. So L1, L2, C3. No, we'll keep it that way. U1, you can rotate like that. And then TR1 there. I think I like that. Now let's see if we can fit the traces through all of here. Well, I'll be. Look at that. I'm a little uncomfortable with having my supposedly filtered and RF clean DC going right next to a pad like that, so I may actually kind of move all of this over. This doesn't need to be centered. And then these can move a little bit closer. No, stop that. Like that. So the RF goes straight through here, through the capacitor, into the LNA. Kind of makes a right turn at the LNA, which you don't like doing, but I'm willing to make some compromises here. That brings that away from that a little bit. Let's extend this down. Oh, no, just kidding. Create a corner, drag it over here. You know what? I think I do want that on the bottom layer as well. Actually, I probably want to keep out underneath that. Probably don't want a ground plane here. Keep out copper fill. Nope, nope, not that one. Okay. Yeah, we'll do that. Okay. And then we'll do that. Via stitch all the things. Oops. Yeah, we'll just do one. Well, look at that. Anything else we should do with that? I think that's pretty good. How long have I been streaming? Looks like, I don't know. It doesn't show me. But I think I'm going to wrap it up. The next thing I need to do is select some components for these outlines and buy the parts and get the boards ordered. I'll probably do that off stream, but when I get these boards in, I will definitely report back on how my egg beater came along. Yeah, and we'll do that. Anyway, I'm Smitty Halibut. Thanks for joining me today. You can reach me at smitty@halibut.com on Mastodon. Or you can post in the comments below, do whatever you want, however you want to get a hold of me. But I'm going to take off. Thank you so much for watching, and I'll catch you later. Be good humans. How far back was my stream? Okay, nope, I'm waving. So